Hi everybody, welcome to this new lecture, Diels Alder reaction. In this lecture, we will discuss about the stereoselectivity, regioselectivity of Diels Alder reaction with a number of examples. First of all, just let's try to understand what is actually Diels Alder reaction. So basically it is not a chemical reaction. Then it is a type of pericyclic reaction. There is a category of pericyclic reactions which are quite different from the chemical reactions. In pericyclic reactions, reagents are not required actually. No acid base is required, no catalyst is required. Just we require a heat or a light. So these pericyclic reactions take place in the presence of heat or in the presence of light. Thermally or photochemically. We will provide heat to the reactant, they will rearrange to give the product. We will provide electromagnetic radiations to the reactants and they will give the product. So these pericyclic reactions are basically of three types. First one is cycloaddition reaction. Second one is electrocyclic reaction. And third one is sigmatropic reaction. Sigmatropic reactions. So all these three types of reactions which come under this category of pericyclic reactions, they take place in the presence of light or heat. They are quite different from the chemical reactions in which we add some catalyst, we provide some acidic medium or a basic medium. Here no need to any acidic medium, basic medium, just requirement is the heat or a light. So this Diels Alder reaction is an example of cycloaddition reaction. So Diels Alder reaction is an example of cycloaddition reaction. So what is Diels Alder reaction? Is a reaction which produce six-member ring. You can say is a very good method to produce six-member ring. So like we have this reactant, this is diene having two double bond. When we add dienophile, this is simple ene, it's called dienophile. In the presence of heat, a six-member ring is formed. The product formed is cyclohexene. So here we have 2 pi and 1 pi, 3 pi bonds total. 3 pi bonds are there. And here we have 1 pi bond plus 2 sigma bond. New sigma bond formed. Like one this sigma bond is formed and second this sigma bond is formed. How this reaction take place? This is just a, you can say, a cyclic of flow of electron. Like these two electrons, they move here. These two electrons, they move here. These two electrons, they move here. Like this. These movement of electron, they take place simultaneously. New bond is formed. If we number it like this, 1, 2, 3, 4, and take it as A and B. So new bond is formed between 1 and A. 4 and B. So just try to find out here. Here your 1 is this, 2, 3 and 4. This is your A, this is your B. Now see, which two new bonds are formed between 1 and A. This sigma bond is formed, 1 and A. And this 4 and B, this new sigma bond is formed. Bond break कौन सा हुआ है? Between A and B double bond था. Now they are a single. 1 and 2 double bond tha, now there is a single. 3 or 4 there was a double bond, now there is a single bond. So this new pi bond between 2 and 3 is formed. So this is now in this reaction, just there is a flow of electron. Now we know that every reaction takes place between one electrophile and one nucleophile. So where the electron density is more, in this reactant that's called diene, we have a 4 pi electron. And in this dienophile we have 2 pi electron. So here this molecule is electron rich. This molecule is electron rich. So it will act as a nucleophile. So your diene act as a nucleophile. And this is electron deficient as compared to this dienophile. As a less density, there is less electron density. So this molecule act as a electrophile. This is your electrophile. So the reaction is between nucleophile and electrophile. Your diene is nucleophile due to the more electron density, and your dienophile is electrophile due to less electron density. So this way, now one more condition in this diene. This diene is called S-cis. S-cis. S means single bond. The arrangement of double bond around the single bond. Through the single bond, double bond. If the double bond are on one side, then that is called S-cis. Cis means on one side, S means single bond. So because there is a single bond between these two carbons, say 2 and 3, there is a single bond. So there is a free rotation around this bond. And one more conformers of it is formed like this. So this is known as S-trans. S-cis, S-trans. They are quite different from cis and trans. You know, cis and trans means we have a double bond and two groups like this. This is your cis. Okay. And if we have like this, this is your trans. This is normal cis and trans. They are interchangeable. Some energy is required because cis is less stable than trans. Because why cis is less stable in this case also, because there are two groups which repel each other. So that's why generally if we want to change the trans to cis, we must require some energy because cis is less stable. When we want to make cis, we want some energy, and that energy is given in the form of heat. Now because in this reaction we require S-cis, basic condition is S-cis. So S-cis and S-trans, they are in equilibrium, but S-cis is less stable. So S-trans is more stable, means generally S-trans exists. So we change to S-trans to S-cis, we require some energy, and that energy is provided by this heat. So the basic requirement for Diels Alder reaction is S-cis, that is in the diene. So S-cis may rotate to S-trans because these two are interchangeable. So you can't say that S-trans is not suitable for this Diels Alder reaction. S-trans can change into S-cis because there is a free rotation around this carbon-carbon single bond. Now next thing is the rate of reaction that depends upon diene, its structure. Because if we have diene like open diene like this, it may rotate. We already just studied that. It may rotate to give a S-trans. So reactivity of this diene, which is open like this, that decreases with this dienophile because it may change into trans, that is more stable. But if this diene is locked, so now I locked diene. This is a cyclic diene. Here, this diene is locked. It cannot change into trans. So its reactivity obviously will be more towards dienophile as compared to this. Because this is an open diene, it may change into trans because trans is more stable. But if we lock this diene, how to lock this diene? Take cyclic diene. So when you take cyclic diene, now this diene is locked, it cannot change into trans. So reactivity of this is more toward dienophile as compared to this open diene. Okay. Now next thing is, next factor which affect the reactivity, because we know that this molecule act as a nucleophile and this is a your electrophile. So any group which increase the electron density on this diene, obviously if some electron donating group is attached, what is EDG? It's electron donating group. If some electron donating group is attached to this diene, its reactivity obviously will increase because it's nucleophile. So more the electron density here, more will be the reactivity. So any group which increase the electron density on diene, that increase its reactivity in the Diels Alder reaction. On the other hand, this is your electrophile. So here any group which decrease its electron density, now we will attach here electron withdrawing group. Electron withdrawing group. So any group which decrease, because it acts as electrophile, it's electron deficient center. Any group which decreases electron density, that increase its reactivity towards Diels Alder reaction. So this is the second factor which affect the rate of reaction, or you can say the reactivity of these two reactants toward this Diels Alder reaction. In case of nucleophile, the group must be electron donating. Any group which increases electron density, that increases reactivity. Any group which decreases its electron density, that increases its reactivity. Now, suppose we have a, say, this is diene, okay, and we have this group. Is it electron withdrawing group? This is your dienophile. This A, B, this is A, this is B, this is your dienophile, and we attach a one group C double bond O. So this group obviously is electron withdrawing. So this group is electron withdrawing group. So it obviously increases its reactivity. More example. Suppose we have this dienophile and adding here C triple bond N. Cyano group. So cyano group is also withdrawing group. So this is your A, this is your B, so it's withdrawing. So it is also electron withdrawing group. So it increases the reactivity of dienophile towards Diels Alder reaction. So now suppose we have this group. This is your diene. What about this? Which is more reactive, this or this? Obviously this is more reactive because this is a methyl group. This is a methyl group. So methyl group give electrons by inductive effect. It's electron donating. So it increases its electron density. So it means its reactivity will increase. The second thing is, suppose we add here like this. So now oxygen has a lone pair of electron. No doubt that oxygen is attached to a sp2 hybridized carbon atom. So this is sp2 hybridized carbon atom. Oxygen withdraw electron by inductive effect. But on the other hand, oxygen has a lone pair of electron, so it donates electron like this. So this is resonance. And in generally speaking, we say that resonance effect is more strong than inductive effect. So overall, this methoxy group is your electron donating group. So it increases the reactivity of your diene. It increases the reactivity of diene. One more example I will take. Suppose this is your diene and we are adding NH2 group. Now in this case also, nitrogen is directly attached to sp2 hybridized carbon, this one. So this is your diene, 1, 2, 3, 4. But nitrogen withdraw electron by inductive effect because its electron activity is more. So can it act as electron withdrawing? No, because it has a lone pair. So it donates its lone pair by resonance effect. And we know that resonance effect is stronger than inductive effect. So overall effect of this group is electron donating. So it acts as an electron donating group. So this is about the group, that how the reactivity of this diene and dienophile that can be increased or by adding some electron donating group to this diene and by adding some electron withdrawing group to this dienophile. Now next is, now this reaction, if we take a locked diene, say locked diene, I said we have three structures like this. Say this is number 1, this is number 2, this is number 3. So these two are heterocyclic compounds, we know. Now when we add dienophile to these compounds, all these three. Okay, so make this little bit more reactive. Say take here ester group COOET. This is your electron withdrawing group because C double bond O is there. Okay, so COOET, COOET, COOET. So electron withdrawing group, look, when attached there, its reactivity increase. Now these are the locked diene. This will be the most reactive. Why? Out of these two, what products are formed here? So first of all, write the first product. So when you heat it, what you will get? So 1, 2, 3 and 4. Okay, and this is your A, this is your B. Where the new bond is going to form between 1 and A? Here, like this, because this bond will shift here. And one bond is formed between 4 and B, like this, because this bond is going to shift here. And this bond is moving here. So can you write the product? Okay, so write the product. Cyclohexane is formed like this. Okay, so this is your number 1, this is your number 2, 3, 4, this is your A and this is your B. Now, which group is attached to A? Is COOET, ethyl group, COOET. Which group is attached? Where is this carbon? Now, the product. This carbon is between 1 and 4. So you can mark here, between 1 and 4, there is one carbon. This. Say this is your 5. Take it 5. So this is your product. So this product can be written by in other ways also. And then because this is a cyclohexane, you can also write it like this. Like this. And here we have COOET, COOET. About the pseudo-chemistry regioselectivity that we will discuss later on. Just concentrate on the product formation, how the product is formed. Now here is your 1, 2, 3, 4, here is your 5, this is your A and this is your B. Simple. So this product is formed. Okay. Now this is a locked diene, cyclic diene is generally more reactive than the open diene because it cannot change into trans. Now what about the other two reactions? Okay. Now in case of second reaction where we have oxygen and here we have a nitrogen. These two are heterocyclic compound. This is your furane and this is your pyrrole. Both are aromatic. Both are aromatic. In case of furane, we know that the oxygen is sp2 hybridized. And one lone pair, this lone pair that is present in sp2 hybridized, other lone pair is present in P. Means the lone pair which is present in P that participate in the resonance, means it move like this. It is a part of delocalization of the ring, which is responsible for its aromatic character. Same here, this nitrogen is also sp2 hybridized. So this lone pair is present in P. This is also the part of ring because it is responsible for the aromatic character of this pyrrole. Now, this Diels Alder reaction takes place when we have an isolated diene. The diene which is isolated. Here the diene is isolated. There is no resonance in this side because this carbon is sp3 hybridized. There is no p orbital. So this diene is isolated. No resonance with number 5. But these two dienes, they are not isolated. They are in resonance with oxygen. This is resonance with nitrogen. Okay, this is resonance with nitrogen. Here it is resonance with oxygen. So when the resonance is there, as we know that oxygen is more electronegative than nitrogen. So what happened? Oxygen attract these p electrons toward itself strongly as compared to nitrogen. So when this oxygen attract lone pair of electron toward itself, it means this lone pair of electron, which is present in p, that is not totally involved in the resonance. Not so much involved as in case of nitrogen. So which diene is more isolated? Just compare these two. It means here this diene is more isolated because this pair of electron that is strongly held by the oxygen, because oxygen is more electronegative. But this pair of electron that is not so strongly held, it get involved. When it get involved, that make this diene, this is a delocalized. So you can say this diene is not isolated. So that's why in the last, in case of pyrrole, no product is formed. Pyrrole cannot undergo Diels-Alder reaction because we don't get a isolated diene here. But in case of furane, because of the electronegativity of oxygen, so oxygen pulls the electrons of this pair of electrons toward itself. That makes this double bond or this diene isolated. When it is isolated, the reaction takes place just like this. But with less reactivity, you can say as compared to this react with the less reactivity. So product formed in this case is again, just draw a cyclohexane ring. Okay. Now write 1, 2, 3. Here is your 1, 2, 3, 4. And here is your AB. So this is your 1, 2, 3, 4. Here is AB. So A is with this group, ester. B is with this group. And where is this oxygen between 1 and 4? So this is your 4. You can write it like this. So in this way we can also compare the reactivity. That when we have a conjugated diene, that is a closed diene, locked diene, that is more reactive than an open diene. But when you compare this diene with this type of compounds which are heterocyclic and aromatic also, so that depends upon the reactivity will be more when we have a isolated diene. When the diene is involved in some resonance, then that's this reactivity of that diene that decreases.